today we are going to look at graphical solution of a pair of linear equations. Recall that we saw three cases for a pair of linear equations. First, where the two lines intersect each other. Second, where the two lines are parallel to each other. And the third case where the two lines are coincident or represent the same line in the xy plane. Now the first case, where the two lines are intersecting each other, the point of intersection represents the solution to these two equations, which means that the coordinates of the point of intersection would satisfy both the equations. Since there is only one point of intersection, there is only one solution. So we call it unique solution. The second case, where the two lines are parallel to each other and do not intersect at all, there is no solution common to these two equations. So this case has no solutions. In the third case, where the two lines are coincident, each point on the line satisfies both the equations. So this case has infinite number of solutions. So intersecting lines have a unique solution. Parallel lines have no solution. And coincident lines have infinite number of solutions. Let us look at the coefficients a, b and c in each of these cases. Now let us look at the ratios of these coefficients. Let us look at a1 by a2, b1 by b2 and c1 by c2 in each of the cases. We see that none of the ratios are equal to each other. Let us look at parallel lines. Once again, let us write down the ratios of these coefficients. We see that a1 by a2 reduces to 1. b1 by b2 is also equal to 1. However, c1 by c2 does not reduce to 1. In other words, we see that a1 by a2 equals b1 by b2. But these two are not equal to c1 by c2. Let us look at coincident lines. We see that the denominator in each of the ratios is twice the numerator, or all the three ratios reduced to 1:2. So a1 by a2 equals b1 by b2 equals c1 by c2. It is interesting to note that just by looking at the coefficients of the xy variables and the constant term in a pair of linear equations, we can conclude whether the pair of lines is intersecting parallel or coincident. Now the cases where the pair of equations has at least one solution are known as a consistent pair of linear equations. Whereas when there is no solution, we call that pair of linear equations inconsistent. Let us look at a few problems. Find out whether the following pair of linear equations are consistent or inconsistent. Let us try to identify a1 by a2, b1 by b2 and c1 by c2 in each of the cases. In the first case, we see that a1 by a2 is not equal to b1 by b2. Let us recall our three types of solutions for a pair of linear equations. Now when a1 by a2 is not equal to b1 by b2, we see that the pair of linear equations has a unique solution. Since it has a solution, this pair of linear equation would be consistent. Let us look at the second case. We see that each of the ratios reduces to 1:2. Hence, a1 by a2 equals b1 by b2 equals c1 by c2. Let us recall our three types of solutions. Yes, this pair of linear equations has an infinite number of solutions. Since they have a solution, this pair is also consistent. Let us look at the third case. Let us identify the coefficients And we see that a1 by a2 reduces to 3, b1 by b2 also reduces to 3. However, c1 by c2 does not reduce to 3. So a1 by a2 equals b1 by b2, but these two are not equal to c1 by c2. Now this is the case for parallel lines, which has no solution. Since there is no solution, this pair of linear equations is inconsistent. Let us look at another problem. Half the perimeter of a rectangular garden whose length is 4 meters more than its width is 8 meters. Find the dimensions of the garden. So we are given that half the perimeter of a rectangular garden, recall that the perimeter of a rectangle is 2 times length plus breadth. Now this is given as 8. Simplifying, we can see that L plus B equals 8. We are also given that length is 4 meters more than its width, or L is 4 plus B. Now how do we find the dimensions of this garden? We could graphically represent these equations in two variables and try to find out the point of intersection. Let us draw a tables for x and y coordinates. Wait, but the variables are L and B. How do we draw the graph in xy plane? So let us replace the length with the variable y and the width with the variable x. Now let us substitute values for x and find the corresponding values for y. For x equals 3, we get y equals 5. For x equals 4, we get y equals 4. Let us look at the second equation. Let us put x equals 0. We get y equals 4. And putting x equals 1, we get y equals 5. Let us plot these points on the Cartesian plane. Let us plot the 2 points for the first equation and draw the line. Let us plot the points for the second equation and draw the second line. Now the point of intersection of these two lines gives me the solution to this pair of equations. In other words, it shall give me the dimensions of the garden. Now, the coordinates of this point, that is x, y, would represent the width and length. So, width is 2 meters and length is 6 meters. Let us look at another problem. Draw the graphs of the equations x minus y plus 1 equals 0 and 3x plus 2y minus 12 equals 0. Determine the coordinates of the vertices of the triangle formed by these lines and the x-axis and shade the triangular region. So we are given two equations and we have to draw these graphs. So let us plot our tables with the xy coordinates. We can represent the y variable in terms of x for both the cases. Let us substitute x equals 0 for both the equations and find out the value for y. Similarly, let us put x equals 1 for both the equations and find out the corresponding value of y. Let us plot these 4 points on the Cartesian plane and draw our lines. Now we have to shade the triangular region between these two lines and the x-axis. This would be the yellow region shown. We also have to determine the coordinates of the vertices of this triangle. So let us label these coordinates and write down the values. So we get vertex F as 2, 3, vertex G as -1, 0 and vertex H as 4, 0.